So in static power, till now we have seen these three things. We know that static power is also called as leakage power, and this three comes under static power, that is subthreshold current, junction leakage, and tunneling current, which is also called as gate leakage. Here these first two comes under intrinsic leakage power, and the third one is called as gate leakage power. Now let us see first one, what is intrinsic leakage power. So here the attribute leakage underscore current is used to represent static current within the dot-lib. Make sure it should satisfy KCL, that is Kirchhoff's current law, that is sum of current entering is equal to sum of current leaving, or else simply if you add the entering currents and leaving currents, it should be 0. So if this is a leakage current, here the above portion you can treat it as positive, bottom part you can treat it as negative, and this point is called as an origin. When you add this above positive and negative, it should be 0. So let us see what is leakage current. So leakage current is an attribute that is used in dot-lib. This is of CCS power format, that is composite current source. So you can take the example of this dot-lib snippet. So suppose cell, name of the cell is my underscore d flip-flop, and leakage current and when condition. When condition means here I am taking two inputs, d and clock. So if two variables are there, we get 4 combinations, that is 0, 0, 0, 1, 1, 0 and 1, 1. So for each and every combinations we get value. So this is state dependent current. When d is equal to 1 and clock is equal to 1, you will get 4 states like this. So depending upon the when conditions, we will get the value. So you can see here PG current with respect to power VDD. So the value is 209 nanoamperes, and PG current with respect to ground, that is VSS, value is minus 210 nanoamperes. Here this value is I static. These are static current values. So this is the static current value, which comes with the attribute called as leakage underscore current. So generally if you add these 209 nanoamperes and minus 210 nanoamperes, it should become 0. But it is not coming as 0. Why? Because there will be some amount of fluctuations that will be happening within the circuit. Now let us see what is leakage power. So till now we have seen leakage current that comes under composite current source format. If it is leakage power, we know that power is equal to V into I. So simply multiply this I static current with respect to supply voltage VDD, so that we get power. So simply I am taking some example of VDD as 1.8 and static is 210 nanoamperes. So simply if you multiply these things, we will get power as 378 nanowatts, or else you can write it as 0.378 microwatt. And this units we need to specify within the dot-lib. So depending upon the dot-lib format, we will get this power as well as current, voltage, resistance, capacitance and all. Remember this point, leakage power falls under NLPM, whereas leakage current is coming under CCS. NLPM means non-linear power format, whereas CCS means composite current source. So see the example here for a cell of D flip-flop. Here leakage power for when condition D is equal to 1 and clock. Here we are getting value as 0.378. Here leakage power unit is in terms of microwatt. Next one, let us see what is cell leakage power. So this comes under NLPM format, which is non-linear power modeling. So example here is AND gate. Here leakage power when A is 0 and B is 0. This is a value. This is A 0, B is 1. This is the value of leakage power that we are getting. When A is 1, B is 0, this is the leakage power value. And when A is equal to 1, B is equal to 1, this is the leakage power value that we are getting. As we have seen, leakage power is equal to V into I. So simply VDD should be multiplied with I static, so that we get this particular thing. And it depends upon the number of variables. As we are going for AND gate, which is of 2 input AND gate, which will have 4 combinations. So that's why we are getting 4 values here. Now let us see how to calculate cell leakage power. So simply cell leakage power is average of all leakage power. So simply you add all the leakage powers divided by number of states. Suppose if you are going for 3 input AND gate, then you will get 2 power 3, 8 different combinations. So add all the leakage powers and divide it by 8. Then you will get the cell leakage power. So this is a cell leakage power that I am getting, and it should be positive. Last one is gate leakage power. So gate leakage power, it comes under CCS power format. So here I am characterizing this particular NOT gate, and this is a driver. So here pin name is A, input is A, output is Z. So here I have mentioned this is a cell that needs to be characterized. So cell name leakage current when A is equal to 0, and gate leakage current, I mean gate leakage Z. So input low value, input high value. So let us see how we are calculating this one. The current which is entering the cell that needs to be characterized is treated as positive, the current which is leaving the cell that needs to be characterized is treated as negative. Means in this, if anything that is entering into the gate is treated as positive and the thing that is coming out of the gate is treated as negative. So simply entering is treated as positive, coming is treated as negative. So entering is positive, coming out is negative. So take this example. So initially I am applying 0 here. If it is 0, this is PMOS, this is NMOS. So PMOS will be on when input is 0, NMOS will be on when input is equal to 1. These are on conditions. So as I am applying 0 here, this is on, this will be off. As this is on, this VDD will be connected to output. So here I am getting VDD, I am taking it as 1. Now this 1 will be applied at here as well as here. So 1 for PMOS, this will be off, and 1 for NMOS, this will be on. So that's the reason there exists a path from this to this towards ground. So in this manner, this one as well as this one gets turned on and it will be connected to ground. So here if you see, the current is entering the cell that should be characterized. So here this is a cell that needs to be characterized. As here it is entering, this should be treated as positive. So current entering the cell to be characterized should be positive. Next, second case, when I am applying 1 here. So 1 for PMOS, this will be off, this will be on. If it is on, it will be connected to ground, so I am getting output as 0. Now the 0 applied to PMOS as well as NMOS. So here this will be on, this will be off. So there exists a path in this manner. Here this will be on and here this will be on. So here if you see, the current is coming out of the cell to be characterized. This is the cell that I am characterizing, and here the current is coming out of the transistor. So here current leaving the cell to be characterized should be treated as negative. So this is the meaning of current entering and current coming out of the cell to be characterized. So input low value means 0, input high value means 1. It depends upon the potential that we are taking. So this is all about power characterization, and we have seen only static power. In that we have seen what is subthreshold leakage current, junction leakage and tunneling, and we have seen different attributes like leakage current, leakage power, cell leakage power, and gate leakage power. So remember these things. So leakage current falls under CCS, leakage power falls under NLPM, cell leakage power falls under NLPM, gate leakage power falls under CCS, composite current source and nonlinear delay model. These two are present, NLDM, CCS. If it is NLPM, it is nonlinear power modeling. So this is about static power in power characterization.